Hey guys, welcome back to the series. So I'm actually recording this ahead of schedule. So from your point of view, it's all going to just be one video, but essentially I'm going to begin this episode by refactoring because I think that I've been like, obviously behind the scenes stuff, I have to be a little ahead of where we are so that I have code to make videos about, right? So I have to be programming, so that's what I was doing this morning. And I've realized that given how we're going to make our parser and the way I've been using grammar as a package, I think it makes sense to sort of just split things out to actually reflect the packages that they're in, so that it's a lot more like a module approach for the record. So what I'm going to do is I'm going to do some package refactoring here. This might get a little tedious, but hopefully it's not too big of a deal. Now, I have just a terminal open in the app, in the like source app directory in the C package. So like the main package, exactly where we are in Vim. And so I'm going to do a bunch of move commands to begin. So let's actually make some directories. I want one for all of our files. We should just have a place for our files. Because like, the thing is, if we look at our Lexer directory, we do have a lot of stuff in there. But token is going to end up being moved into a grammar directory so that it matches its package, right? That way, all the grammar has access to one another and we don't have to do a ton of imports. It's just convenient that way. When it comes to source file and source line, those could stay in like a Lexer directory, but our parser isn't actually going to have anything other than itself, because the node is going to be grammar and every node we make is going to be grammar. And previously I was nesting all of the nodes inside of the parser directory, but that just doesn't really make sense because the nodes also transpile themselves, and it's like it just doesn't really conceptually make as much sense. So I think doing this refactor is going to help us. So like I said, we have a files directory, we also want a grammar directory, and we want a stages directory. So grammar is where all of our nodes, our tokens, are going to live. Files are where most of our files are going to live, our source file, our debug file, and I'm also going to throw the source line in there because it's almost like a component of the source file. In fact, how big of a file is this? Because you might want to just merge it into, I have to do Lexer / it might be better to even further refactor and put that inside of the source file. Although it is kind of large, so I'm fine keeping it separate. I don't really care too much. But now we have those three. Again, we should just start moving things. So I want to move the debug file into our files. So that cleans up our main directory a little bit. And then, of course, we have to move some stuff from Lexer. So let me just see what's in there. And we want to move Lexer / source line. We want to move the source line into files / source line. And we also want to move the source file into files / source file. We want to move the token from inside of our Lexer. If you're doing this using a GUI, it might even be easier, but I'm just doing this with commands. I'm sure you can follow along the refactoring process. And keep in mind, right now we're just moving files, which won't actually break anything because of how Kotlin works. All of these things, it's not like folder. The folder doesn't matter so long as it's inside the thing. So long as it's inside like the package, it still has a package declaration. So we'll actually have to go through and change those as well, which will be a little tedious, but I think long term it'll be worth it. So let's look at our Lexer. Well, we want to get rid of that as well. We want to move that into the stages, because that's one of our stages, you know, being the Lexer, the parser, the transpiler, and any in between that we might make, like a borrow checker, for example, or a type checker, or maybe a publisher, so that you can do like importing, exporting. I just call it publisher. So some of the naming thing, my whole idea is, I'm trying to find words for the stages so that the stage order is the alphabetical order, which is why I've chosen, well, Lexer and parser is fine, right? That's sort of familiar. And then those are alphabetical, and then I can put a publisher in between parsing and transpiling, and then I can also put like a scrutinizer or like something like that to be the type checker or whatever. But anyway, that we're getting ahead of ourselves. We want to move lexer into stages. And we want to delete the lexer directory now because we don't need it. So our directories should all be good if I use tree, which is a super useful command, which also prints sort of a tree structure. This is exactly the way I'm going to print our AST, by the way. This is how I'm going to have our nodes print out, except obviously the color I'm not going to do. But so you see, this is the structure that it should be inside of our C package, which is just, it's a super useful way to display this. So now I can actually go into Vim, and you see it reflects, the changes are reflected here. Currently nothing's going to be broken. But you notice I was importing Lexer, everything from Lexer here, and it was kind of weird. There's not really a good order to start changing these things in. I don't think, anyway. Let's start with files, but the thing is it's going to break everything, so you kind of just have to keep moving. So this is no longer package C, this is package C.files. Same thing with these. No longer in the Lexer, it's part of the files. And if we go into the last one, the source file. So just all three of these we can just change to this. That shouldn't break anything inside of these three, because the source file needs source lines, but they're in the same package still. It's just a different package now. Okay, that's all of our files done. And this was a harder refactor for me on the other side, because I already have like some nodes and stuff. So it's actually a lot more work. But okay, now we want... This is fine, but we have to change the import. The token is staying in the grammar 1, but now we have to import c.files.sourceLine. Why is this complaining? It is subtype property. Oh, because Oh, because we didn't change it in false yet. That's okay. Yeah, see what I mean? You're going to get a lot of errors, so you kind of just have to ignore most of them. So we've done files and grammar. Let's just go into our Lexer and change that. Instead of being its own package for some reason, let's just add it to a general stages one. We can still import the token, but now we also need to add 2 more imports because we need access to source file and source line. So we have to import files.source file and source line. And so that should fix most of that. Inside of our app, instead of importing the Lexer, we can just import all the stages. And now we won't have to make declarations to import the others, and we're not importing stuff we won't actually need, which is super useful. There's one other thing we need in here, though. We needed the access to the debug file. So we can do c.files.debug file. I'm going to move that below, even though it's not alphabetical just because of width. It doesn't matter, though. And the only thing we should have to change left is our faults. And instead of importing source line from Lexer, we should be importing it from files. And hypothetically, this is right, but it's very good that I'm in the wrong directory. Okay. It's very good that we should test this to make sure it actually still works. So at least for me, everything is linked up correctly now. So once again, just essentially, let me print out, do I still have it or did I clear it? I cleared it. So let me just print out again, app source main Kotlin C. This is what your structure should look like. If this structure is good, and if you go into each of these and you just modify it so its package is the folder it's in, then everything will work so long as you change the package declarations and the imports. So I think that's going to be it. And now I will edit in the rest of the episode. So now we can actually begin work on our parser. But before that, there is one small refactor that I want to do. I would have included this in the first section, but I actually did it after I finished filming that, so I didn't realize. But so currently on the left, what we have is we have a stage map in a companion object. So it's essentially just a static property of the faults class. But this is kind of stupid, just because then however many stages we're going to add, we're going to have to come into this object and modify them. And we can probably just do better than that. So how about instead of repeating ourselves, how about the lexer knows that the verb to use is lexing, and the parser knows that the verb to use is parsing, and they can manage the setup themselves. So what we want to do is essentially just delete this companion object, and we can modify the stage property to just be a stage verb instead. Because that's all we really want, is just a verb, so that when we have errors, it says what we were doing. For example, like a lexing error or a parsing error, so that the user knows which stage it occurred in, which might be useful. And it's useful for us in terms of debugging. So now we can go down to act, and instead of referencing the map, we can just reference the stage verb. And the last thing we can do is remove the increment from finished stage down here, because we don't need that anymore. And that should be the only changes we have to make to the defaults class. But now we have to make changes to the lexer. So what we need then is just an init block. I always press the wrong one. We just need an init to run at the constructor. Let me just see exactly how I formatted it before. That's how I thought. And we can just say false.stageVerb is lexing. And then every component we have, every stage, will have this block at the top that will just set its verb here. And then we can manage it, like it makes sense, right? Like the lexer should be handling the fact that the verb should be lexing, instead of the false object managing that itself. And that way, if we change the order for some reason or something, then the verb will change with it, and we don't have to rely on a map. Okay, let's save that. And now I think we're ready to start work on our parser. So what we can do is, in our stages directory, we can construct a new file, parser.kt. We can add it to the c.stages package, and we're going to need some imports. So we're going to need kotlin.math.min, I think anyway. Yeah, we will. Okay. That's just a useful sort of thing. We don't need it, but it's useful. We're going to need our false object, obviously. We're going to need c.grammar.token. We'll need access to the tokens. And the last one we're not going to worry about yet. But essentially, the way this is going to work, in a broad outline sort of way, our lexer is responsible for making every single token. You could split that up so that you'd have individual, like, punctuator token class or module, and you could use the lexer as like a toolkit to then build tokens. But in our case, we're just using the lexer to build everything. Now, when it comes to the parser, I find it makes a lot more sense if the parser is more like a toolkit. The parser doesn't make everything, but each expression in our grammar is going to have its own node class in our case. Could just be like modules or functions if you don't want to use OOP type stuff. But they will then reference the parser, and they will know how to make it themselves. So that means our parser can actually be pretty lightweight, whereas our lexer was like 300 lines, our parser's like 47, which is just, you know, it's just how it ends up working out. So we can make this a data class called parser. It obviously needs the false object, and it also is going to need a list of tokens, which I'm going to make private. Personally, we can add methods to sort of like reference it, but to me it just makes sense to make that private. We could always change that if we need to. Similarly, we need that init block from before to set the stage verb to parsing. And now we need some variables. So we need an index in this list so that we know where we are, because the way we're going to work is we're just going to iterate through the list one at a time, and so we'll have an internal index to keep track of that. And eventually what we'll do is we'll produce a tree, which that actually should not be private, because that's going to need to be referenced outside eventually. But we don't need to really worry about that. I'll just leave this here, because again, we don't have our file statement. And what a file statement is, it's essentially the highest level of our grammar. So it represents the entire source file, like you can imagine this being a source file. And all it's going to have is a list of statements. And so we'll construct that, and by extension, that will construct the rest of everything. So eventually we'll store that as the tree. We want to implement a way to print this out, so we'll have a toString override, which is just going to end up printing out the tree. Right now, we can't do that, so I'm just going to print out the word tree. But once we actually get the variable, I mean, what I could do is I could just temporarily make this tree variable like 0, just for now, just so that we can set this up. And then we'll have a public method called makeTree, which will be which will call tree dot, and then we'll have a method that makes the tree. So actually, yeah, I think at least this one I'll comment out, but I'll write it in. Tree.makeTree using this parser. And our file statement's going to be the only node that has the makeTree method in it. There was a reason I set it up that way, but until we actually make nodes, I won't remember why. Okay, so now we can actually get into like the utility functions of this parser. You can think of it as a big toolkit. So one of them is a head, which is going to be kind of similar to things we've done previously, but what this is going to return is it's going to return the tokens that are, well, specifically it will return one token, and it will be the token that is at this like index ahead of where we currently are. So for example, ahead 0 will return the token that we're currently working on. Ahead 1 will be the next one, etc. And the reason I'm using min here is just so that we don't have to worry about if we accidentally make the I too large. So we can just take the minimum of I plus n, which is where we currently are, plus n, which is exactly what we want, and tokens.size minus 1. This way, if our I plus n is way too large, then we're just going to return the last token in the list instead of indexing something that doesn't exist. Then we can define a field, which will just be ahead 0. Like I said, it's just the next token. So we'll be able to say things like parser.next. Then we'll have a take, and this will return a token. This should be pretty obvious what you expect this to do. It will store the next token, it will increment the I, and then it will return the token. That's all it's doing. And then there's some useful ones. So there are times when... So with the toolkits that we've set up so far, we can do things like if parser.next.has, because our tokens will have like .has methods on them, and that's why I gave them this, so we could do something like this. If parser.next.has this, then we could do something with it, right? If the next token is an open parentheses. And so that's why I'm setting this up this way, so that you can just read it like this. That's why I made next a field, for example, so we don't have to do that, because it just doesn't look as nice as this. If parser.next.has this, then we can say parser.take, for example. And we can just work with that. Now that's all well and good, but that's like a conditional sort of logic. Sometimes you want to guarantee that there is a symbol. So for example, if we had our parser.next.has open parentheses, well, we could, let's just say we'll like do stuff, and then after we want to say, well, if there isn't a closing parentheses, then that's a problem, right? Like we want to guarantee that there's a closing parentheses, so we'd want to throw an error. But it would be annoying if every time we had a situation like that, we had to throw an error ourselves. So what we can do is we can make this expecting of method, and this should do kind of what you would expect. And notice that there's an expecting of and expecting has. So these are just going to utilize the token of and has methods, except we're expecting that that is true. So if it isn't, there should be an error. And initially we're going to take in a variable number of arguments, just like the lower ones, just like the of and has methods. So we're expecting that the next token is going to be of one of these types that we're passing in. And so what we can say is if next dot of one of these types unpacked, we can just return it by taking it. Otherwise, we throw an error. And we want this error to kind of look reasonable. So what we can do is we can take our types and we can map them, and we can get their name from them. Because, trying to remember, we must have set up these token types to have names. I'm actually curious. Let me see exactly where that's coming from, because if I don't understand it... So we have, let's see, on the right side, we're passing a bunch of token types, it.name. Do those even have... Interesting. I'm very confused where that's coming from. So it seems like the name property of an enum is just a thing in Kotlin, because this error clearly works. So I guess I'm just not going to worry about it too much. Whoops. Let me just head back now. Hopefully I'll edit out all of those few minutes of me just trying to figure that out. Anyway, let's just go back. So what we can do is we can map all of these enums. And then what we want to do with a map, because this is going to produce a new list, the list of all the names, we can just join them to string, separated by commas, prefixed with square brace, and postfixed with ending square brace. So it just looks like it's a list of things. Then we can say throw false.fail. We take the token as the thing that has the problem. Expecting type of names. So we're just saying, like, expecting one of these things in this list. It's not the best, it's not the most, like, attractive way to display that, but it works. So then similarly, we can make an expecting has. Get rid of that line. Var arg with values, and those are strings, and this will again return a token. If next.has unpacked values, then we return the token. Now, since we have the values, we don't actually have to map them to get the names. So we can say that the vals are the values.join to string, and the exact same format from before, so it looks like a list. And then we can throw false.fail, take expecting value of $vals. But there is one thing we have to do. Oftentimes, if we're looking for a new line, we want to be able to say, like, parser.expecting has this. But this is a literal new line character, which is good because that will match against the token. But it's bad because if it prints it out, it's going to print it as a new line. So we just need to replace that with an escaped version so that it will print out /n instead of a new line. And lastly, there's just a handful else. We want an expecting of, but this one that takes in a collection. I don't remember, did we... Let me quickly just take a look in our token. Did we do that with this as well? We did. Oh, well then that changes my implementation here. So, again, it's just useful sometimes to be able to pass in an entire collection. And what I can do... Oh, I see. Yeah, so it's still easiest for me if I just utilize the previous one, so that I don't have to retype the thing. But what you can do is you can cast it to a .toTyped array, and then you can unpack it. Any collection. At least the ones we'll be using. I don't know if there'd ever be an error with that or not. Doesn't seem like there'd be, if you believe the type system. And then similarly for expecting has, we want a collection of strings, and we can just do the exact same thing calling has c.toTyped array. And lastly, oh, there it is. Lastly, what we want is just a quick little skip new line function. And all this is going to do is if next.has a new line, we just take. And if our lexer were worse and we had a bunch of new lines, you'd have to make this a while loop. But since I changed that, we can just check if there's another one, we just take it and do nothing with it. Because, for example, we'll utilize this when we're doing something like this, 5 plus 2. After we get the operator, we can then skip any new lines so that we don't have to worry about it. And if there is one, it will skip it. And if there isn't one, it will do nothing because it's conditional. Let me go over here. And if you need extra time to type, this is a good time to get caught up. Maybe I'll put them all together, even though they're kind of unrelated. And for now, at least, that's our parser. We'll have to come back here once we make the file statement so that we can hook it all up. But as far as I know, these are all the methods that we need. We could add more in the future if we find that this isn't enough. But it's really simple. It's just a very, limited toolkit. And that's kind of all we're going to need. So it looks like, I don't remember how long it took to refactor. It's probably like 10 minutes. So I'm assuming my recording right now is at 19. I'll cut out like 2 minutes or something. So I think we have time to work on our nodes anyway. Right now in our grammar module, we only have tokens. So let's actually build our node. But first things first, on the right side you see, this is where we're going to be utilizing Kotlin Reflect. So let me go back up to our build.gradle. This should already be here from the first episode, but just make sure you have this line, implementation Kotlin Reflect. If you're using not Kotlin script, it will be a different syntax, but just make sure that however you have it, you have Kotlin Reflect in your Gradle project, because this is where we're going to be using it. So now we can make a node.kt file, package c.grammar. We'll need to import Kotlin reflect.k class, which allows us to reference classes as like a variable, and import Kotlin.reflect.cast so that we can cast between classes. Do I need that? Actually, I don't think I ever ended up using that. So let me just quickly, I'm pretty sure, no, I don't. I used it once upon a time, but I didn't get rid of it. So we don't need that, good, nice. But what we will need as well is import Kotlin.reflect.full primary constructor, because we're going to be implementing a binary operations class, because a lot of our nodes are going to actually be binary operations, and the construct logic is the same for all of them, so there's no reason to actually just repeat it in like 10 files when we can just have it here once. And I will say, this implementation of mine with nodes, it will have a lot of boilerplate. You're going to have a lot of classes, but I think in the end it's going to be worth it, because each node will be responsible for making itself, for type checking itself, for borrow checking itself, and for transpiling itself. And so you don't need all that logic somewhere else. You can just make one contained thing to do everything for that node, that expression in the grammar, and it can handle it for you. So initially it's going to look like a lot of boilerplate, but eventually it's going to hopefully be useful. If we get to the end of this and you find that you could write it better, then feel free. So we need our faults as well, and we're going to need access to a source line because we're going to reference that like once, and we want access to all of our stages. Technically we don't need the lexer, but all of the other stages we will want. So first things first, let's make a type alias, and we're going to call it parts. It's not the best name. You could call it something else, but you'll see in a moment what we're using it for. Essentially, it's just a list of false components that are nullable, because that's what our nodes are going to have as properties. They're going to have a bunch of tokens and a bunch of other nodes, but we don't know which, so we're just going to use the common interface. We're allowing them to be null because sometimes it's useful. Oh, what's a good example? For example, consider this expression in our language, right? Var x equals 5. Well, if this could be like a variable declaration statement or something, right? But it has some optional components. For example, you could specify the type, but that's optional if you have a value on the other side. And the value itself could be optional if you specify a type. So those nodes are going to need some optional things, and instead of doing conditional logic to check if you have it, which is, I've done that before and it's kind of a pain, we can just pass in nulls into our list of things. So let's make an abstract class. This is kind of annoyed me because it's really close. We were really close to being able to make node an interface, but because I want to override toString, it didn't let me. But at the end of the day, it really just doesn't matter. Making an abstract class, it's not going to really affect much. So it's an abstract class called node, and of course it is a fault component. And we're going to have an abstract value parts called of our type parts. And again, you can call this whatever you want, but we're going to have to override this in most of our classes. So I just want something really easy where I can just say like this, parts of type parts is a list of something. Like that's all I want to do because it just makes it easier, which is why I don't want to have to type list fault component. And then if I did that, I'd have to import c.faults and everything, and that would be a huge pain too. We want a type, although we don't have to worry about that yet. That's going to be for later when we actually do the type checking. So I can ignore that for now. So the way that static properties of classes works in Kotlin is kind of weird, right? We've been using these companion objects. And if we're making an abstract like class so that we can inherit stuff, or we can like implement methods for like polymorphism or whatever, we can't directly do that with companion objects. We can't enforce that an abstract class must have a companion object, which must then have methods. But what we can do is we can make an interface called companion object, or whatever you like it to be called. And in here, this is an interface that then we can optionally inherit from or extend. What's the word? Implement. That's the word. Implement. So in our subnode classes, we can make companion objects, and we can inherit from node.companionObject, and that will enforce that the class will have static methods. We can't enforce that every node does that, but we can choose to do that because the way we're constructing nodes is actually going to be a static thing, right? We're not going to be calling the actual constructor of the class. And the reason for that is some of the way our grammar works, right? If I quickly go show you again, by quickly I mean very tediously, the way that our grammar works, you see it looks like this. We have this thing, or it could just be this thing. Meaning each of our nodes could return itself, an instance of itself, or it could just return an instance of another type of node. So if we did that in a constructor, that wouldn't really work because the constructor will make a node of itself, but it's not necessarily going to need to do that. So the way we're getting around that is we just have a static method that will construct nodes. And it's still a property of the class, so the class will know how to make itself, but then it might just return something else. And actually, while I'm here, I'm also going to add the exponential expression that I'm going to add. I believe, I don't actually think, I might have to look. I don't think I made it this priority though. And sorry for the quick derailment of this whole video, but. Okay, so I have to. Get rid of that. Okay. We have to change the multiplicative expression to reference the exponential. This is just, the reason I'm adding this is for two reasons. One, it makes me feel more justified in changing XOR because we're going to use the caret symbol for exponentiation as God intended, obviously. And also, it's just a good showcase of going right to left, and it's a good showcase of our type system in the future. So this is just going to be a cast expression, and it's going to look just like the others, except the optional thing is on the right. And that's literally it, because you can see then it will go right to left doing this. And, if you're not following along with the grammar, that's not a big deal. We're not really worried about that just now. But once we have our nodes in place, that will be the next step. Okay. We head all the way back in here. And, okay, we're still on our interface. And I call it construct. I've called it make in the past, and I've done tons of stuff actually, but I just call it construct. And of course, it needs the parser passed in. So it's going to construct itself using the parser, or it could construct something else, which is why the return type is just node. Now it is nullable because sometimes it's useful for statements or like types or whatever to return null if they didn't construct, but our expressions are just going to return a node. And the useful thing in Kotlin is that node is a subtype of nullable node, which means we can implement a constructor that can only return a non-null node, but it can still like inherit from this or implement this and have no problems. Because of course, yeah, node is a nullable node. Then we want, we don't have to worry about verifying yet. That's going to be part of the type system. So for now, we're just going to construct things. Now we have to override our fault component properties. We technically don't have to override these, but we have an implementation, so there's no reason to do it in every subnode. We want access to our lines, which is, it's a value, which will return a list, and it's a getter because it's a field, not a property. And what we want to do is we want to make a mutable set of source lines. And then what we have to do is for part in parts, so we're looping through all of the components of this node, and we're using the, I forget the like safe chain, whatever, this syntax is to say that if part is null, we do nothing. Another thing you could do is you could do filter not null here, and then you wouldn't have to worry about it. But to me, this is a lot less typing, so I'm just going to do it this way. And if that thing isn't null, then we can utilize the value. And what we want to do is we just want to add the lines of the part into this mutable set. So it's going to recursively call this until it gets down to tokens, because it's always going to eventually trickle down to tokens, which is going to return a single line. But for all of our nodes, it's going to have to return a big set of lines. And I'm using sets because you might have multiple tokens on the same line in a node, and we want to get rid of those duplicates. So we're going to reference the part that isn't null. We're going to take its lines using recursion, and then we're going to cast it to a set. And then we're going to just add that to our current set. And at the end of all this, we have the set of all the lines without the duplicates. But what we really want, since we're going to use this to print out errors, we want them in order. So we can return lines.toList, and then we can sort it, sorted by, and we're going to sort it by the line number, which makes sense, right? Because the line number should be in order, and we know the number of each line. So that's how we'll be getting all of our lines. It's really small because it's recursive. And then we can have a tree string. This is really why we have the tree string at all. The token just like prints out itself, but this is where all of the sort of meat of our tree visually comes from. So we want to make a string, and we'll end up returning it. The string initially is just going to refer to the class name, because each of our classes is going to be things like an additive expression or something. So we can print that out, and we can access that name by doing this, : class.simpleName. And that will just print out its name, or, well, it will store it in the string. And then we need all of the parts, but we need to do parts.filter not null, because we want to remove all of the null components. And we're using this syntax instead because we want to loop through with indices. And if the indices would all be messed up if we had null components in them, so that's why we're filtering. And we can get both of those, parts.withIndex, so that we have our index and the part. And the reason we need the index is so we can say, technically we could do this other ways, but the way I'm doing it is we need to know if we're at the end of the tree so that we can change the symbols that are there. Again, I guess I can come up here and say tree this, because this is essentially what we're printing out. And so what I mean by at end is, are we here? That's the end. Because you can imagine this is 1 part, 2 parts, 3, 4, and 5. And the subparts don't matter. Once we're at the end, we need to change from this symbol to this symbol. And as we go down, we need to add these, and we have to do all this. And so we have to know if we're at the end. And when are we at the end? We're at the end if I, the index, is parts.size minus 1. Technically, I think we could also just say parts.last, and we could compare against that. But this works. And then what we want is our symbol. So if we're at the end, we have that symbol. I'm going to leave these in the description because they're very specific symbols. And if you don't want to just like... it took me a long time to actually find these like proper symbols. So I've just been copy-pasting them ever since, every single time I implement this. Okay, so if we're at the end, we have that corner symbol. Otherwise, we have the down symbol, which you can see here. And because these symbols are so tall, it looks gapless, which is why we're using them. Val child symbol is... So the child symbol is going to be this over here. Because, for example, you see these need these because there's things below, right? It needs a vertical connection. But down here, there's nothing because it doesn't need a vertical connection because there isn't another part. So what that means is if you're at the end, you don't actually need that. So we can just set it to a space so that it's because the width needs to be correct. Otherwise, we can use that vertical symbol. Notice it's actually not the just like normal vertical bar. It's slightly taller. So copy it from the description, I recommend. Easiest way to get it. I don't know exactly what the symbol is otherwise. Otherwise, we use that symbol. Okay. Now we have to recursively get access to the children. So we have sort of like this type of thing going, but what we need is this. We need to recursively go down the tree. So we can just call that something like children, and this is going to be part.treeString. So we'll call treeString on the component, which is why our tokens need tree strings as well. And what we want is we want our prefix, so the thing that follows before, to be the current prefix, so that it's the same, plus the child symbol, so that it has like all of... It's hard to see with this because there's only 2 levels, but you can imagine that if there's a 4 indent before the symbol, and then this is the child symbol. And then what we want is 3 spaces. That will align things exactly like this. Because you see here, 1, 2, 3, and the 4th character is that. So it just makes it look pretty nice. And I'm really glad that this tree function exists. Not just for like files and stuff, but it's exactly how we're going to be printing our tree. So it's a great visual indicator. And then what we want to do is we want to just add on everything to our string, which is the prefix. And notice I put a new line here. Prefix, the symbol, a space, followed by all of the recursive children. And it will just return that. Oh, I have an equals here. And that's our tree string here. Now, there's 2 more, right? We have 2 more things we need to override from the default components. We need our mark, which is pretty easy. We just say parts.forEach, so we just loop through. We can just say take each part, and if it's not null, we mark it. So if it's a node, it will just call this again, and if it's a token, it will actually do it. And everything will filter down to tokens. And we want to implement our toString so that we can just print out nodes. And that's really simple. We'll just call the tree string, but we'll give it a prefix of 4 spaces. And I recommend typing 4 spaces rather than a /t, because the /t sometimes or often prints out 8 spaces in terminals, so I'd rather just be explicit about my spaces. And actually, I think that's it, because the verify node thing is going to be for later. So that's all we have so far for our nodes. It's just going to have a bunch of parts. We don't know what those are specifically, because each node is going to have different types of parts. And we have all of our methods. So actually, the only things currently we have to override in this class are going to be the parts field, or actually it is just a property, and the construct method. And that's it, because everything else has an implementation. And we can override those implementations, and let's give an example of that. So let's make another useful abstract class called PrimaryNode. And these are going to be for things like all of our primary expressions, maybe not all of them, but anything that essentially just takes a single token and it inherits from node. And we can override the parts to just be a list of the single token because it's one token. And we can change the tree string so that it looks a little bit nicer, because if you only have one property, it would be kind of a waste to do this whole indent thing, right? So we could just put it on the same line. So we want to change the tree string. Still takes in this prefix, and it's just going to return. I think I'll just copy this whole line. It's going to return the simple class name plus a space followed by this unique symbol. So I'll also have that in the description, followed by the token. So it will just print it all out on one line because it's compact, right? We don't want to waste space. And here comes the big boy. So now we actually want to have a binary operation node like I explained before. Abstract class BinOpNode, so binary operation node. It's going to have a left component, a token as an operator, and a right node. And this thing itself is a node. And since we're at the width of our line, I'm going to do this. Because, I mean, I'm just like, I don't know, it's obviously like a choice. It's a stylistic sort of, it's supposed to be a guide. The like 80 character limit, it's just supposed to be like, keep this in mind, but I prefer to do this, I guess. It's at least probably better for the video because we only have one character cut off now in terms of the width. Anyway, every binary operation node is going to have the same 3 parts, so we can override that so we don't have to implement that every time. It's just a list of left, op, and right. And now what we want is we actually want to, since this binary operation node is going to have the same constructor, that's all well and good. But we want to interface with it in the subclasses in a way that sort of makes us have to type the least. So what we want are some static properties of the class for every subclass so that we can reference them here, override them in the subclass, and then, utilize them. This sounds all very abstract, so maybe in a moment we'll make like one node as an example. But we'll make a new companion object interface, which is an extension of the node's companion object interface. And this is going to be, we're going to have 3 main properties that we're going to be overriding. So when we write something like a multiplicative expression, we'll just have to define these 3 properties, and then we're done for the constructing and the parts. So we need a reference to the class so we know exactly what object to make. And we could store this as a k-class of type any. Notice that the way that k-classes work, if I make this like a k-class of BinOpNode, a k-class of a type that, suppose we have some class B, or I guess multiplicative expression. Multiplicative expression is a subclass of BinOpNode, but k-class of multiplicative expression is not a subclass of k-class BinOpNode. So basically what that just means is we have to make it of any type. We can't do any sort of like inheritance stuff with the reflection here. Then we need a has list, which is a list of strings. So notice again, has, we're going to be doing like parser.has. And this is going to be a list of all the like accepted operators. So for example, with multiplicative expressions, again, it's going to be times, divide, and mod. And lastly, we need a method or a function to make every child node. And that's going to be a function that takes a parser and returns a node. Again, it could be a nullable node, but all of our expressions are going to not be that, so then we actually have to override our construct, which will return a non-null node. And this is just the general structure of a left to right binary operation node. You make a child, which is the thing on the left. using the parser. And while parser.next.has, the has list, you can do stuff. But suppose that it doesn't, right? Suppose that you don't have any of those operations. Well, at the end, we're just going to return the node. So if there are no operations, so if it's something like 5, right? You'll try and make a multiplicative expression, but there are no multiplicative operators, so we'll just return the 5. But if there then is one, we can go into this loop, and we can say op is parser.take, and then I'm going to say parser.skip new line, because what I want in my language, I don't necessarily want new lines to be available everywhere. So for like this, I don't want that to be an expression because it's not really readable. But oftentimes, if you have like your width is too big, I think this makes sense because you're expecting there to be more. So I'm personally going to choose to skip new lines after the operator of every binary operation. And then what we do is we have the operator, we skip the new line, then we can make the write, which is again going to be a call to make child using the parser. And then we have to make the node. And this is why we need class.primaryConstructor. We have to assert that it's not null, and we can do a call on it, which will pass it in the 3 left, op, and right things. So the node is the left, op, followed by right, and then we have to cast it to a node because it doesn't know what type it is. And that's it when it comes to that. So let's actually like go in and make an additive expression just so you can see what it's going to look like. I have to go out of here. We're in the grammar directory, so let's now make a subdirectory called expressions just so we can sort of keep things neat, but they're still going to be in the C.grammar package. We can make a file and call it AdditiveExpr.kt. This will be in the grammar package, as I said. We want to import all of our stages. And now we can make our class. So this will be an additive expression class. It needs the 3 properties, left node op token, right node. And it's going to inherit from binary operation node, and we have to pass in the left op and the right. Now, because binary operation node overrides parts, we don't have to worry about that. But we do need our companion object, which will inherit from BinOpNode.companion object, or I suppose it will implement. And you see there's a problem here. It's telling us, which is why we have this whole setup. And so we just need these 3 properties. Class is going to be additive expression class. You reference it like this, you don't do that. You use the : syntax, so it actually has it's set up the right way. We need the has list, which is just a list of plus and minus. And then we need override val make child, which for now I'm just going to refer to itself, so it's not actually going to work. But the way you have to set these up is you give your class that you want for your child. You have to say .companion : construct. And this will reference the construct method that we're implementing from our companion objects. So I ran into some trouble before where I was trying to just say additive expression : construct. But you have to, for this type of reflection, you have to explicitly say .companion for this, and then it will end up working. And so that's just how we just constructed our additive expressions. Once we have the child ones in here, then we're literally just all set. So let's try and get a few more of these then. Whoops, classic. Primary expressions are going to be a bit of a pain. So let's just go sort of, maybe we can work our way back up. And like I said, it's going to seem like there's a lot of boilerplate. So let's make an expression.kt to just represent expressions. Package c.grammar. Import c.stages.parser. And I'm just going to have a class to represent every part of our grammar. So in this case, it's going to be an abstract class expression because our expressions don't actually exist, they're just a representation of other classes. So we can have an abstract class that inherits from node and make the companion object exactly the way we would anticipate normally. And we need to override construct in here. And all this is going to do is return AdditiveExpression.construct using the parser. And so the question is, why would you bother, right? Why bother making this whole abstract expression class? Well, because in our grammar, sometimes you just want an expression. So since everything's in the same package, if you're somewhere else, you can just say expression.construct parser, and you'll get some expression because we've set this up this way. Now we have to work again back up. The next high thing is actually going to be a statement. And I don't know, I think I will do some of those because again, it's really like tedious. It seems like boilerplate because it is. We need a statements directory actually. And actually, I haven't shown you this grammar yet, so we should probably actually look at that first before I actually implement it. Docs grammar. We can make a statements.ebnf, and it's going to be the top level, like I said, is a file statement. And this is going to be a bunch or none ended statements. Ended statements are statements that use a line end. And our line ends are going to be semicolons or new lines or end of file. And the reason I'm defining it this way is so that when we have other types of statements, it's going to be nice to be able to put them on the same line and for our grammar to represent that well. Something like an if statement followed by another statement here, followed by an else on the same line, then our statements can't have these line ends as part of them, which is why I'm making ended statements a thing. They'll add the line end to the statement. And then we'll have actual statements. Again, it's because of the way that the grammar sort of works that we'll end up with the boilerplate that we will. I'm not going to worry about any of those statements yet, but we could just have basic statements to begin with. But you see, eventually we'll have certain loop statements. Basic statements are going to be expressions, for example. So I think we can leave it there for now. And this is sort of why we have boilerplate. We're going to have basic statements, which could be multiple things, but they could also just be an expression. And then a statement can be multiple things, but right now it's just a basic statement. Ended statements are going to be that with a line end, and the file statement is a collection of all those things. So now we can head back into our statements. Let's make some of these. Make a new file called BasicStat.kt. Package c.grammar. Import c.stages.star. Abstract class, because again, these things don't exist, they just reference something else. At least for now, they don't exist. In our basic statement, companion object, this is going to get very familiar very quickly. We're going to override fun construct, parser, turning a node. And eventually, I am going to actually introduce a print statement. So rather than do functions, at least just very initially, while we work on expressions and all the type stuff, we'll have expressions that are like this, or maybe like this, you know, I don't know, I haven't decided exactly. It will probably just print a single string. And so you can see that on the right side there. But for now, our basic statements, I mean, technically I should implement that, shouldn't I? So if parser.next.has print, then we can return a print statement.construct parser. Otherwise, we're returning an expression.construct using the parser. And we can also implement the print statement, which will be a concrete class. Print statement, it will just have an expression. It is a node. So we have to, this is how most of our classes are actually going to look. We need to override val parts of type parts. It's going to return a list of expression. You probably could do reflection instead of this, but I'm not very good at reflection and it might end up being a hassle, and it might be very language specific, which is why I'm also choosing to do things this way. We have to override our construct using the parser, and this will actually give us a good use of how our parser will work as well. So we could just say parser dot, since up here, right, in this class we're checking if there's a print, then we can just return. We can either take it or we can expect it. I'm choosing to do expecting has instead of just take, because if for some reason we make a print statement some other way other than basic statement, then this can return, and this could hypothetically throw an error. It will guarantee that it's actually constructed properly instead of just taking something and having our tree messed up. This will actually throw an error. And then we have to make an expression. We just construct it using the parser, and we return an instance of the print statement storing that expression. Okay, I hope this isn't too tedious, and I hope this also isn't turning you off from this whole series, because I think long-term it's going to be beneficial to have all this. Next is the statement. Percent just stat.kt. It's in the grammar package. We need all of our stages for the future. I guess I forgot to change that over here as well. And this one's an abstract class, at least for now. Companion object of type node.companionObject. We need our constructor. Return node. And we're just returning a BasicStat.construct, because again, it's just like, you could think of this as like a redirection, at least for now, because it's only one thing, but in the future there'll be multiple here. So we're just setting it up for then. We have ended statements. And then we're almost done with all this boilerplate stuff. But once it's written once, we can just edit it. We don't have to do it every time. Import C stages.everything. Again, I need to change that. Because that way, by importing all the stages, we don't have to modify these classes as we add stages. They'll just have access, which is why I did the refactor. So EndedStat, it just is a statement. And you want to make sure that all these nodes have like at least one property so that you can print them out for, we need access to the parts to do the like tree representation. So I'm not going to store the like the line end character, but you could, and then you could print that out too if you wanted to. Override parts, type parts, which is a list of the only one we have. And you might even want to just copy paste this when you make these. But I've been typing this for so long now that I'm just like so used to it. Okay, so for this constructor, what we have is a node, and we're going to say statement.construct using the parser. Parser will be expecting has token.lineEnds, which is why we put that in the token class. And then we can return the ended statement. So quick overview. We're making a statement, we're expecting there to be one of the line ends, and then we're just constructing this. We'll also have to add some stuff to our token class in a minute as well, but we're almost there. It's definitely a big episode, I think. We need to now make our final file statement. Now this is going to be slightly different. It's in our grammar as well, import c.stages.everything. Have to change that. Not very good at Vim. Class FileStat node. Now, we're going to store all of the statements in this thing privately. Because again, file statement is just a list of statements, so we want a mutable list of type node. We want our parts, which is kind of funny, right? So we're storing the statements as a mutable list, but we're just setting our parts to the statements. And actually, it doesn't need to be a field because it's always going to have that list, right? The list is going to remain the same. So it can just point to that. It's just a pointer. I'll change that over here as well because I don't think that needs to be a field. So it's private, but we're also just like directly giving it, but it should cast it to, or actually it's not going to be exactly the same, right? Because this is a mutable list of type node, but we're going to be returning it as a immutable list of type fault components that are nullable. So here, we're not actually going to have that companion object because we're not going to be constructing things the way that other nodes are constructed, which is why we have a make tree here, because this is going to make everything else. And we're taking in the parser. And basically, while parser.next.has end of file, while it does not have an end of file, we can say parser.skip new line. So if there's a new line, we just don't care. And then if parser.next.has an end of file, so for example, if you had a new line followed by an end of file, then this is what we're detecting, so you break from there. Otherwise, we just make a statement, and we add it to our mutable list, and we just say statement.construct using parser. Although I suppose it should actually be EndedStatement.construct, because that's actually how we set it up. So that should be all of those like basic sort of statement things that we just need for this. And now we can actually go into our parser again, and we can actually use the file statement. Just have to go up to the top. There should just be an import c.grammar file statement. And our tree needs to just be an instance of file statement. We're then printing it out. And then when we say parser.makeTree, it's going to just say tree.makeTree using the parser. So that should all be well and good. If I forget, is it? I don't remember. There's a command. Control U. Okay. If we just try and build this, we haven't actually linked up the parser yet. Okay, so everything built correctly. Let's go into our tokens, because we have to add some stuff down here. One of the operators I added, like I said, is exponents. We haven't actually made the node for that yet, but we can add the symbol here. And we also want to add a new keyword, print, because we're going to be using that eventually. So our Lexer needs to support that, so we can just come into here and modify these lists. And that's why I put these here, so that we can just have one place where all of this is represented. All right. I think that's going to be fine. In fact, we could probably make those other nodes. I mean, we're already this far in. But first, let's link it up in the app. So, since we're importing all of our stages, yeah, I actually do. I'm going to move this up here. It doesn't really matter. Since we have all of our stages imported, we can just immediately come down here. And it's going to be replacing this comment. Now we can say, we can make a parser of type, obviously parser. It needs two things. It needs faults, and it needs access to lexer.tokens. And then if run parser, which we haven't written yet, it will take in the parser and the debug file. And if it fails, then we break. And this is important, even when we have our last stage, we need to do this. Because if there's a failure, this last line is going to run again and print the warnings twice, which isn't good. So we can make our run parser very similarly to before. We can just reference the parser, take the debug file, and we can utilize the run stage that we have before. Again, we access the faults through the object. In this case, we're not going to print anything because we're like in the middle of processing, but we could just say parser.makeTree, and then we can write to the debug file ast:/n, followed by, that looks like 4 spaces, followed by the parser.toString. So let's try it again. And you see we have a file statement, but there's nothing there. So if we actually, I could probably just come in here and say vim test/file.lang. Did I never change that extension? Because I did, no, it shouldn't be. It was always .c in here. Because before in the other one on the right, I was using lang instead of c just because I wasn't sure, but now I am. Vim, let's just go into test file.c. So we have additive expressions. I don't think we did the primary expressions though, which is kind of the pain because it's really hard to test all of this without this. But let's just see if any of the errors work. We write this, and we quit and build it again. Right, because the additive expression is referring to itself because we haven't actually implemented those other nodes. So I think I'll just make this one really large episode, and we can just go do that. We can implement those last few ones, just so that it's all, just so we have something printing that isn't failing. I don't want to leave the episode like that. So we can make multiplicative expressions. That will be next. And in fact, let's go into our additive and actually change it. So the child of an additive should be a multiplicative. It's going to complain because it doesn't exist yet. MultiplicativeExpression.kt. Package c.grammar. Import all of the stages. And we make it very similarly. Left, which is node, op, which is token, right, which is node. It's a binary operation node, left, op, right. And we need our fancy companion object that does basically all the work for us. Override val class is itself multiplicative expression : class. The has list is going to be slightly different. And in fact, because of this, this is the reason I didn't bother making these lists in the token class, because you could have separated all the you could have separated the operations or the punctuators into like binary operation, but we never actually use that because we just define it here. Because if you have like 3 or 4 operations, it's just not a big deal to type them out here. And this is going to need an exponential expression dot companion dot construct, so that it will try and make those. And go in here and do that as well. Exponential expression.kt. This is going to be similar, except it's not. Because this is going to be right to left. And in fact, it's the only binary operation that is right to left. So I'm just going to essentially write it from scratch rather than try and do anything fancy. So we have to manually override our parts. Parts type parts is a list of left, op, right. And notice I made this a data class. Maybe I'll slow down just a moment. Hopefully it's not been too fast. companion object, which will be the node companion object this time. Object, that's good. Object. And now we need to write the construct by hand. It's going to be very similar, but actually, it's going to be easier if anything. I guess. So, we start off very similarly. We make a node, which will be a primary expression. It's technically going to be a cast expression, but for now, we're just going to go right to primary expressions. And instead of doing it iteratively, because it's right to left, we can actually just do it recursively. So if there is not the exponential operator, we can just return the node. Otherwise, we can take the operator, parser.take, we can say skip new line, and on the right, we can then, recursively say exponential expression.construct, and you could just say construct here, but I prefer to say exponential expression.construct just so it's clear that it's being like recursive. And then we can actually utilize the constructor here and say node op right. So you see this time the thing on the right will be the exponential expression, whereas before it would be on the left, because that's just how it's set up. And lastly, we need to make our primary expressions. There's a lot of these. I think I should probably just make them all. PrimaryExpression.kt. So here is going to be a good use of why we have, or a good example of why we actually have these abstract classes. So we need access to our faults because the primary expression has its own error. And we need all of our stages. Now we can make an abstract class primary expression of type node. Companion object of type node.companionObject. We can override the construct parser. And what we want to do is we want to utilize parser.next, but I'm going to write this as a when expression. So just to sort of simplify things down, I'm going to say parser.next.let, so that we can just refer to parser.next as it. So when it is of token type num, we can then, for example, make a NumLiteral. Let's come down here and define that. It's going to have a token, but it's also going to have an imaginary optional token. So we could say it's a primary node, but it's actually not really. But we can sort of change that. And the way I'm doing imaginaries, in a lot of languages it could be something like in C it's 5J. I like I because, math, not engineering. But the way I'm doing it is instead, you saw I didn't add anything fancy to our lexer. What I'm doing is, in our language, if you have a number followed by an identifier, that doesn't make sense in any context. So if there is an I following a number, which means it could be like this, for example, there could be spaces or whatever, then I'm just going to interpret that as the imaginary component of that number. Okay, so we need to override val parts. And this is also good because it means I don't need to use a keyword, because if you have a language where I is a keyword, that's going to suck for looping. It's too useful of a variable name. And so here's an example. Our imaginary is optional, but we're just adding it into the list because who cares? We managed all that in the node abstract class. We then want to modify our tree string because there's actually like two things here and one of them's optional. So it's this class.simpleName followed by those fancy symbols that I need to copy every single time. Followed by the actual token, and we have image question mark dot let, so that if it's null, it won't call let, right? And we can just say it's nothing. But if it isn't null, then we can do a space followed by it to actually print it out here. And now we actually need to construct these things. Parser node. So val num is going to be parser dot. We're expecting it's of type token dot type num. And then for image, we could just say if parser dot next dot has an I, then parser dot take. Otherwise, it's null. And the reason this works, like initially when I was doing this in the very beginning, I was trying to compare token types and values all the time, but what I realized is there's nothing that's ever going to, there's no token that's going to have this string except the identifier. So you don't need to always check types. It's useful for something like a number because that could have a string containing anything. But for identifiers that you know, like that's why I implemented the .has anyway. And we can return the NumLiteral, num and image. Those are our numbers. There's something super crucial we should probably just add now, and that's our primary expression error. These are things where, like, what if you wrote something like 5 plus, what's a good example? If. Like, if you wrote 5 plus if, right? That makes no sense. In Kotlin, it kind of does. But in our language, if you said, like, 5 plus some keyword, that makes no sense. Like a while. 5 plus while. Like, that makes no sense. So if there's a token, the way that's going to work is it's going to trickle down into the primary expression every time. And so we need an else here to say, well, maybe there's a token here, we have no idea what it means. So let's just take it. Then we could throw a failure with the token. Unexpected token in primary expression, followed by the token. Okay. I mean, we're already this far in. Oh, God. I think that's probably going to be it, because this will bring us enough to actually test, and then in the next episode we can continue with those. Jeez. Hopefully this hasn't been too crazy. Now if I build it, there we go. So you see our list of tokens. It's a number 5 plus a number 6, new line, end of file. And what that's going to build is a file statement, which has an ended statement, an additive expression with our number plus number. And so you see, because we have our parts as a list, it will print them all out like this. You see that NumLiteral's a primary node, so it will print it out like that. It has no imaginary component, so it's all fine. We could go and change that. Let's just add an I here, so that now it's actually a complex expression. We do it again. You see that it just changes, so it represents it like this. So I think that's a reasonable way to represent it. It's nice and compact, but you still see the fact that this one's imaginary. And you can see it's printing them out as tokens. So you can directly compare, okay, this one ended up here, this one ended up, was from there. And so you see our tree, it looks lovely. And I think it's a pretty good representation. Remember, this is being written to a debug file because we're using the debug option as we run this every time. But let me print out c.bash just to remind you exactly what we're doing. This tree is inside of the file.cdebug because most people aren't going to see it. But personally, when I'm building this, I like to always see it. It's really satisfying to see every single time for me, because then you know that your structure is correct, because we built all of this work to make this structure, and this tree string method actually displays that it's being set up correctly, and you can see all of the parts, every property that it has, and I really like that. So I hope you guys have followed along just fine in this episode. In the next one, we will, I suppose, continue making the rest of these primary expressions, and maybe some other expressions, because I think there's other things in our grammar I haven't implemented yet. And then eventually we'll be able to do the next phase, which will be type checking. So I hope you guys are having fun. I'll see you in the next episode.